Okay, I don't know if you have any questions from last class. Is it clear where the methods come from? I do have the, what is it? Yeah, it was. Yeah. I sent it to professor. Maybe he haven't, because I don't have access to Canvas, so I couldn't upload it. Maybe he hasn't done it yet. Where is here it is. So a brief summary of it. It's related to chapter 4, numerical integration. So we studied 3 methods to solve a set of n equations. So we start from this. So at some point we have that x point equals f of x. That's a vector function. So f is a function of x. X is a vector, an n-dimensional vector. So we have n state variables x. So we have f. F is going to be a function of those n variables, x1, x2, up to xn. And we want to solve this. And in the general case, when that function is nonlinear, we have to use numerical methods. Otherwise, it's going to be almost impossible to get an explicit solution. As we can, with a linear system, we can do that. But with a nonlinear system, which is the case of a power system, we have to use numerical methods. And we relied on the Taylor expansion of that discretization of that function to come up with 3 methods. One is called forward Euler method, which is also called a direct method, where every next step it's computed based on the previous step tk. So we know, let's say, the initial condition to 0. Based on that, we know the initial state x0, x of t0, and we add h times the derivative of h, which is given by the function f, at that time 0. And that's how we compute the next step. And when we do that recursively. And there are other methods that we study too. The backward Euler method, which is an implicit method. Now we use, instead of the derivative at time tk, we use the derivative at the next time. So we have to solve a nonlinear set of equations to get the xk plus 1. We have to solve for those. And normally here you're going to have a nonlinear equation too, so you have to do any nonlinear method to solve that, which is one of the things that we're going to discuss. And the trapezoidal method we told to be basically an average of the forward and backward Euler. So it's an implicit method too, because we have to solve for that x of tk plus 1. So what we're going to do today is to use MATLAB to compute the solution of this simple example 4.1. Okay. So here in the lecture notes, you can check the results. It's everything done by hand, basically. So what we want to do is to put this into MATLAB and make sure that we understand how to use these numerical methods, because it's something very important to solve a bunch of equations. And next class, we're gonna look at how to solve this kind of system of equations, but using a MATLAB function called ODE, which is mercy. First question, do you have any experience with MATLAB? Are you comfortable with it? Somewhat. You know how to make vectors, matrices, multiplications, plots, functions?
We were never formally taught MATLAB, but we had to learn a good bit last
semester. Good to know. So we're gonna start with this system. Yeah. First of all, what we can say about it, it's a linear system, right? So if we want to, we can find the exact solution, which is something that you already did in example 2.13. You used, I think, the eigenvector decomposition to get the solution. So what we're going to do is we're going to get something approximate to that exact solution. So we know what the solution is, and we're going to use the forward Euler, backward Euler, and trapezoidal to approximate our solution to this thing that we know that is exact. We can come up with some conclusions about it. So let's go to MATLAB. Say example 4.1. Can you see? So I always start with something like this, clear all CLC. So we clear all our workspace and our common window. And now we're gonna start with some initial things, right? So we have, what do we have here? So consider the system discussed in example 2.13, the state space model. So we have some matrix A, we have some initial condition, and we need some time window. In this case, it's gonna be 3 seconds. So we can simulate from 0 to 3. And let's use the same thing. Then we can change all the variables, but let's start with what is in here. So we start with an h equals 0.05 and n steps, 60 steps from 0 to 60, right? So let's put that information in here. So we're gonna have some t0 equals 0. We're going to have some final time equals 3. We're going to have a time step equals 0.05. And we have n steps, which in this case we can do, let's say, TF over H. That is going to be 60. Should be 60, right? Yeah, it's 60.
Is this thing important?
Yes.
Okay.
Yeah. Thanks. Okay. Yeah, that's what I was thinking. Let's stop. Give me a second. View. Do you see the option here anywhere?
If not, it's okay.
Maybe we can do this. This is going to be the same. Oh, I forget how to do it. Okay, let's go. Okay. So we have our initial data. We have our time vector. Let's say we're gonna go from T0 to TF in its steps of H, right? And we have some initial condition X0, which is gonna be according to this 1, 1. So we're gonna have some vector 1, 1. So just getting the initial data, we have 60 points that we have to calculate or approximate with these methods. We have this time vector from 0 to 3, and we have our initial condition. So first of all, let's get the explicit solution. So the explicit solution, according to the notes, is this, right? So we have some point of comparison. So square root of 10, exponential of minus 2t, cosine of 3t, 1 plus 1.25. So it's gonna be square root of 10 times the exponential of minus 2t cosine of 3t plus 1.25. And the x2 is exponential, I have it here, exponential of minus 2t minus 2t times cosine of 3t. There you go. So, so that x1 and that x2 is going to be a vector, right? Because t is a vector. That's why I'm adding that point here. This is going to be a vector point-to-point multiplication. So we're good. We have vector x1, a vector x2, and we have a vector of t. And we can get some plots from here, right? So let's see the solution. So I'm gonna do a subplot, let's say figure 1. And we're gonna plot t x1 in, I don't know, black. And let's say we're gonna put some title. And this is gonna be x1 of t. And the other figure is going to be quite the same thing. X2 now. And we're using the second figure. So are you familiar with this subplot thing? Right? So it's going to be a grid of 1 by 2. The first one is going to be x1. The second one is going to be x2. And we should be able to plot this. And we get the solution. So the idea is now to use the numerical methods and see what we get from the results. As we kind of explained last class, we should get an approximation for this. So it's not going to be exact. And it also going to depend on the time step that we have. So that's another thing that we can play with. If we increase the time step h or we decrease that time step. So that's the exact solution or point of comparison, let's say. So number 1, let's say forward Euler method. For the forward Euler, we're going to start with some x equals x0. So we're going to have some initial condition load into this variable x, which is going to be the solution for this method. And we're going to go from, we're going to use the same k. K equals 1 to n. Here should be the formula for the next step. So let's say x, both solutions, x1 and x2, for the step k plus 1, the next one is going to be, what is it going to be? Okay. So x of k plus 1 was x of k plus f of x of k t k times h. How do we do that? So in our case, it's going to be the next one is going to be the previous step, right? So it's going to be x of k plus f. What's going to be that f? Remember, we have x dot equals ax. This is our function f of x. So what do you think it's going to be? Just ax, right? So it's going to be the previous step plus a, some matrix, times x, that one, times h, right? So and that matrix is this one, -1, -10, 1, -3. -1, -10, 1, and -3. And that's it. So when we do this for the whole interval from 1 to n, then we should get our 60 points that are going to represent our solution. So we can do, let's say something like, let's do a hold on here. And do the same thing. So now instead of x, we're going to plot the first component, all the columns. And here's going to be the second component, all the columns. And this is going to be, I don't know, blue. So we can know which one is which. Right? So let's see what we get. What does it say? Oh, this k plus 1. It's k here. You see? So we have the exact solution, the black one, and the approximated solution using the backward Euler method. And I said that this is an under, what did I say? It's an under approximation, but that's only when you have this kind of behavior, right? But the right thing to say is this function in blue, it's lagging the black one, right? Mm-hmm. And the backward Euler should be leading the explicit solution. But it's a kind of a good approximation, right? It's just the first order, is the most simple thing that we can think of. So that's for the explicit solution of the first one. Let's do the second one. Backward-Euler method. So let's rewrite, let's reuse the same X here. Let's use the same structure, 1 to n. And what do we have to do now? That's the big question here. What can we do? So we're going to have something like this, right? This is the forward Euler, backward Euler. So x of k plus 1 is going to be x of k plus a times a plus 1 h. Right? So how do we move this thing to this side? Now, can we do that?
Well, oh yeah, I can. It's row that we have to define.
So we have to get something to x k plus 1 equals something that depends on the thing that we already know. So it's going to be minus a x k plus 1 h equals x. What is it going to give us? I minus a h x of k plus 1 equals x of k. And then we can get the inverse of that. There you go. So we have, let's say, the inverse of something, which is going to be the identity of 2, right? Wow. Minus a, and what is a? Maybe we can define a here, because we're going to use it all the time. So we can use a here. And minus a times h. What's the inverse times the previous step? And that is going to be this thing. That's pretty much it. So let's see what we get. I'm going to copy the same code for plotting this solution. And I'm going to use, I don't know, red. There you go. It works. It works. So the last one. This is a pretty easy exercise. And as you can see, TRM is triangular rule method. So I better put forward Euler, backward Euler. And this is the triangular row. So let's do the same thing, but now we have to get the expression for that x of k plus 1. What is it going to be?
One half the inverse identity inverse. You say that you have the backwards order plus one half. Then you say we'll have the second order.
So k plus 1 or h over 2 f of k xk ek plus f of k plus 1. Let's do like this. F of k plus f of k plus 1. Right? So we're going to have x of k plus 1 equals x of k plus h over 2 a x of k plus a of x of k plus 1. Right? So we're going to have x of k plus 1 plus or minus here this multiplication h half times this to this side. So we're going to have a h over 2 x of k plus 1 equals x of k plus h over 2 a x of k. So now we can take the inverse of the resulting thing. That is going to be I minus a over a h over 2 inverse times this vector here, which is going to be x k plus h, or we can do that. I plus h over 2 x k. And that is going to be our right-hand side here. So why do you think we can do this in this simple system? Can we do this kind of solution every time? For any system that we have? Because we have this system now, and we can solve for that implicit method. Can we do that all the time? What can be a case that we can't do that explicitly?
If you have if the A matrix is dependent on will it always be a coefficient matrix, or will it have could have state variables in it?
I mean, if that matrix depends on T, for example, if you have T here, can you still do that? I don't see any problem, because that A is gonna still depend on T at the time K, or TK, right? So you can still do that, because that is gonna be a linear system. It's gonna be a time varying linear system, but you can still do that. But if you have this plus x1 squared, for example, then you're done, because that's a nonlinear system, and you cannot apply that thing to. So this formulation that we're doing is kind of simplified exercise, because this is a linear system, and we can do that. But in the case of a linear system, we can't. But let's do that here first. So what do we have? The inverse of something. So I plus h over 2 times identity matrix plus a. This is a minus sign. This is plus a h over 2. And what else? X. This x here. And let's see what we get. If we did it right, then we're good. We're good. So what you can see from the solution? What can you tell? So the first of all, the black one, it's almost together with the explicit solution, right? So now same question. What we can tell about the solution?
That is always a very good approximation.
That's yeah, exactly. Very good approximation. And as we said, it's kind of the average. Can you tell that? It's kind of the average of those two. It's where the method comes from. Now, and the other thing is that the forward Euler, it's kind of lagging the actual solution, and the backward Euler is kind of leading the solution.
The midpoint between leading and lagging solution.
You get, yeah.
Really?
So those three methods are quite simple, and because of that, they are almost never used. It's a good way to understand that you can take this Taylor expansion and come up with a method, an approximation of that function. And in this case, we're using just the first derivative, just the linear term. And there are a bunch of other methods that uses more than the first derivative, and you get a way better approximation. Way better approximation. So one thing that I want to do is to let's see what we get if we change the h. If we make it bigger or smaller. Let's say we have 0.1. What can we tell? So what did we do? Instead of having 60 points between 0 and 30, now we have half, right? So we have 30 points. How is the approximated solution? Better or worse? Worse, right? Exaggerated. And if we take more points, let's say 0.01. How is it going to be? The approximation is going to be better, right? It's not that the resolution is better. It's that the method is closer to the actual solution. So that's an important thing to know. It's that when you have this methods, the time step that you take, it's really important. It's really important. So that's pretty much the example. I can send you this after the class. And there is something else. Well, you can look at the example here from the lecture notes, And you can tell that how it's presented is to get this matrix, but in an explicit way. What we did here is just replace the matrix equation, and we get the solution. That, for example, this is the, which one is this one? Is the backward Euler method, and that's the matrix that you get. And that should be equivalent to what we got here. That matrix I minus A H. You can try that out, but it's gonna be the same. So I have some small presentation here that I would like to go with. So numerical integration methods. So we talked about the forward, backward Euler, and trapezoidal, and those are very simple methods based on the first derivative. This one is also based on the first derivative, but it's a more complicated method. Just like in the trapezoidal, we use let's say an average between the Euler and forward and backward Euler. This one uses a bunch of derivatives. I'm not trying to prove this method and how it works, but you can tell that it uses the first derivative at tk, the same as the forward Euler. It uses the first derivative at time tk plus h, or t0 plus h, tk plus 1, right? And some intermediate derivatives. And this is what is called the fourth order Runge-Kutta method, and this is a very good approximation of a solution. The error is pretty small, and also you can see that it is a direct method. It's the same as the forward Euler, because you don't have any k plus 1 on the right-hand side here. So you don't have to put that thing on the left-hand side and try to solve for tk plus 1. It's a direct method. So you can put those equations just as we did with the forward Euler, and you would get your solution. It's pretty straightforward. So that one is the one that is mostly used almost in every application. So some notes that I wanted to add in this thing. So the difference between the exact solution and the approximation that we're getting, this curve here, smooth curve, is going to be the exact solution, and the most that we can get with our method is going to be just some straight line, right? Some initial point plus the derivative. So that is going to give us some error, some what is called the local truncation error. So the forward and backward Euler, they have an error of h squared. What does it mean? Does it mean that? It means that when you have a polynomial of degree 2, then when you have a polynomial of degree n minus 2, h to the n, then this method can approximate that exactly. So if your exact solution, it's a straight line with some slope, then the backward or forward Euler is going to be the exact solution. You're going to have 0 error. However, the trapezoidal has an error of h cubed, so it can approximate the a parable, let's say, a second order solution polynomial exactly. And you can think of what's going to happen with this Runge-Kutta. This is the fourth order Runge-Kutta, so it's going to be, its error is going to be on the order of h cubed. So wherever that it's bigger than a fourth order polynomial, it's gonna have some error. That's what you get. And there are